This method is for the resolution of hyperstatic structures, whether beams, frames, or reinforcements. In this method, rigidity factors are used, of which there are 4 key models. 2 are for angular rigidities and 2 for linear rigidities, since these depend on the different models. In other words, we could say what type of support does. The factors depending on the models are the following. For a built-in model with a simple support and its angular displacements, at an embedded end, the moment is 2AL, and at the end, with simple support, the moment is worth 4EIL, for a model with 2 simple supports and with angular displacement. At the end, where the angular displacement is applied, the coefficient is 3EIL square. For linear displacements, we have the following model. For the double recessed model, the linear rigidity coefficient at both ends is 6EIL2. For the following model, it is embedded and with simple support, which has a linear displacement, delta. At the embedded end, the stiffness factor is 3EIL2.
And what happens if we have a distributed or point load on our beam? Do moments change? What is its value? Referring to Gonzalez Cuevas's book called Structural Analysis, on page 347, it tells us what the moments of embedment are. As you can see, the terms it uses are W, what is the load, L, which is the length. So with this, we proceed to calculate the moments at the 2 ends. There may be a case in which we have a hyperstatic beam which has more than 2 simple supports. In this case, the middle supports are changed and embedded to make use of the method. So the first section is articulated, embedded. The second, built-in and built-in. The third is embedded, articulated. And with the same methodology it is solved, we separate the original beam into 3 simple beams, and now we solve beam by beam, making it simpler. Once we have all the moments, we add them at each point of intersection. The moments calculated at node A, at node B, and at node C. We call these nodes moments or unbalanced forces. Since these moments do not exist in the original beam, since the moments at its supports are equal to 0. Now we have to restore these moments that we generated since they should be equal to 0. Now we put into practice the angular stiffness coefficients, returning to the example of the beam with 3 simple supports. I have to release degree of freedom. By degree of freedom, just as I restricted or embedded them. In that case, we embed the node or support in the middle, so that is where the moments we are looking for are generated. Having all these moments or unbalanced forces previously calculated, the linear and angular ones. Now we will write the equilibrium equations, adding the moments of imbalance and setting them equal to 0, since in the original structure the moments are equal to 0. And with this, we can calculate the value of the turn at any node. We will have as many balance equations as nodes that we have restricted or embedded. That is, if we restrict 3 nodes, then we will have 3 balance equations. If we restrict 2 nodes, then we will have 2 equations. Therefore, we can solve these equations in a matrix way or substitution, as the case may be. Now that we have solved, we solve or calculate the angular displacements with the help of the equilibrium equations. We will proceed to calculate the corrective moments that will help us correct the imbalance that we generate when embedding or restricting the nodes. To calculate the corrective moments, we will multiply the value of the angular displacement that was calculated previously by the angular rigidity coefficients of each node that we restrict, to finally give us the moment that will correct us. Having all the corrective moments, we will proceed to calculate the final moments, which are the sum of the embedment moments plus the corrective moments. We will do this sum in each node. It is important to note that these final moments must be the same, but with the opposite sign to the previous one. Having everything right and fulfilling the above, we proceed to calculate the reactions by applying the superposition. We can solve by saying the complete beam in smaller beams and then add the results. With this, we would calculate the reactions in each node and proceed to calculate the axial, shear, and moment diagrams.